Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome to our deep dive into neural networks. We'll be exploring their history, their inner workings, and their impact on various industries.
Yeah, we've got a fascinating journey ahead of us. We're going to be tracing the evolution of these powerful tools from their theoretical beginnings to the cutting-edge AI applications that we see today.
So let's start at the very beginning. Where did the idea of neural networks originate?
Well, the concept of neural networks, it can be traced back to 1943 with the work of Warren McCulloch and Walter Pitts. And they developed a mathematical model of artificial neurons. This laid the foundation for the field of artificial intelligence.
What was groundbreaking about their model?
Well, their model demonstrated that, in theory, a network of artificial neurons could perform any logical computation just like the human brain. And this was a revolutionary idea at the time. It kind of suggested that the brain's intricate processes, they could be represented by mathematical functions.
So this model, it essentially planted the seed for the idea that machines could think like humans.
Precisely. It opened up the possibility of creating artificial systems capable of learning and problem solving, much like our own brains.
That's incredible. What happened next in the development of neural networks?
Well, in 1949, Donald Hebb, he introduced a crucial concept, it's known as Hebbian learning. His principle, often summarized as neurons that fire together, wire together, offered an early understanding of how learning could occur within neural networks.
Can you elaborate on Hebb's principle?
Sure. Hebb's principle, it suggested that when two neurons are activated simultaneously, the connection between them strengthens. And this implies that repeated coactivation leads to the formation of stronger associations, essentially mimicking the process of learning through experience.
So it's like saying the more you practice a skill, the stronger the neural connections associated with that skill become.
Exactly. This idea was fundamental in shaping our understanding of how neural networks could learn and adapt.
So we had the theoretical foundation laid by McCulloch and Pitts and the learning principle introduced by Hebb. When did we see the first attempt to actually build a neural network?
That came in 1958 with Frank Rosenblatt's development of the perceptron. It was one of the first attempts to create a machine that could mimic the human brain's ability to recognize patterns.
Was the perceptron a success?
Well, while it could recognize simple patterns like shapes, its capabilities were limited. It struggled with more complex tasks, leading to a period of disillusionment and, reduced interest in neural network research.
What were the limitations of the perceptron that held it back?
The perceptron was essentially a single-layer neural network, meaning it had an input layer directly connected to an output layer with no hidden layers in between. This limited its ability to learn complex, nonlinear relationships in the data.
So it was like trying to solve a complex puzzle with only a few pieces.
Exactly. It simply didn't have the complexity needed to handle more intricate tasks.
So what brought neural networks back into the spotlight after this period of disillusionment?
The answer lies in a technique called backpropagation. Although the concept had been introduced earlier, its significance wasn't fully realized until the mid-1980s.
Can you explain what backpropagation is and why it was so revolutionary?
Backpropagation is an algorithm that allows neural networks to learn from their mistakes. It involves calculating the error between the network's output and the desired output, and then using this error signal to adjust the weights of the connections between neurons.
So it's like giving the network feedback on its performance and guiding it towards making better predictions.
Precisely. Backpropagation enabled the training of multi-layer neural networks, meaning networks with hidden layers between the input and output layers. This added complexity allowed these networks to learn more intricate patterns and relationships in the data, overcoming the limitations of the perceptron.
So backpropagation was the key to unlocking the true potential of neural networks.
It was a major breakthrough. It revolutionized how neural networks learned and paved the way for the rapid progress we see today.
This brings us to the late 1980s, right?
Yeah.
What were some of the key developments during that time?
Well, the late 1980s, we saw the emergence of convolutional neural networks, or CNNs, pioneered by Yann LeCun.
What made CNN so special?
CNNs were designed specifically for processing data with a grid-like structure, like images. They employ convolutional layers which learn to extract features from local regions of the input image, making them highly effective for tasks like image recognition and object detection.
Can you give an example of an early successful application of CNNs?
Sure. LeCun's LeNet 5, it successfully demonstrated the real-world applicability of CNNs by reading zip codes on mail. This was a task that had challenged traditional computer vision techniques. It showcased the power of CNNs to handle complex image-based tasks.
So CNNs marked a significant step forward in the field of computer vision.
Absolutely. They revolutionized how we approach image-based tasks and laid the foundation for many of the image recognition and computer vision applications we see today, from facial recognition to medical imaging.
What other important developments emerged around this time?
In 1997, Sepp Hochreiter and Jürgen Schmidhuber, they introduced long short-term memory networks, or LSTMs.
What problem did LSTMs address?
They tackled the challenge of memory in neural networks. Previous architectures, especially recurrent neural networks, struggle to retain information over long sequences, limiting their ability to understand context and perform tasks like language processing.
So LSTMs gave neural networks a better memory.
Exactly. LSTMs were designed with a special memory cell that could store information over extended periods, enabling them to excel in tasks involving sequences, such as understanding the nuances of human language, translating languages, and generating text.
This brings us into more recent times, right?
Yeah.
What were some of the defining innovations of the 2010s?
The 2010s saw an explosion of innovation with several groundbreaking architectures emerging. One notable development was the introduction of generative adversarial networks, or GANs, in 2014 by Ian Goodfellow and his colleagues.
I've heard about GANs. They're known for generating incredibly realistic images, right?
You're right. GANs consist of two competing networks: a generator, which creates data, and a discriminator, which tries to determine if the data is real or fake. And this adversarial process pushes both networks to improve, resulting in the generation of highly realistic and creative outputs.
So they basically play a game against each other, with the generator trying to fool the discriminator and the discriminator trying to catch the generator.
Precisely. This adversarial training process has led to remarkable advancements in image synthesis, style transfer, text-to-image generation, and even the creation of art, pushing the boundaries of what's possible with AI-generated content.
What other groundbreaking developments emerged during this period?
In 2017, the transformer model, it emerged. It revolutionized how neural networks process information, particularly in the field of natural language processing.
What made the transformer so revolutionary?
It introduced a novel mechanism called self-attention, which allows the network to focus on different parts of the input data simultaneously. This enables parallel processing, making training far more efficient compared to the sequential nature of previous architectures like RNNs.
So transformers sped up the learning process significantly.
Yes, especially for large data sets. The transformer paved the way for groundbreaking language models like GPT-3 and BERT, capable of understanding and generating human-like text with remarkable accuracy.
It's incredible how rapidly these models have advanced.
Yeah.
It feels like every few months there's a new breakthrough.
And the pace of innovation continues. In 2019, diffusion models entered the scene, offering a novel approach to generating high-quality images.
How do diffusion models differ from GANs in their approach to image generation?
Instead of generating images directly, diffusion models start with random noise and gradually refine it, step by step, until a clear image emerges. It's like starting with the blurry picture and slowly bringing it into focus through a series of refinements.
That's a very different approach compared to GANs. What are the advantages of using diffusion models?
Diffusion models have shown impressive results in terms of image quality and diversity. They often surpass even GANs in certain aspects, making them ideal for creative applications and pushing the boundaries of what's possible with AI-generated imagery.
So we've seen a remarkable evolution of neural network architectures, from the simple perceptron to the sophisticated diffusion models of today. What are some of the key takeaways from this journey through history?
Well, one key takeaway is that the field of neural networks is characterized by continuous innovation and refinement. Researchers are constantly pushing the boundaries, developing new architectures and training techniques to address limitations and unlock new possibilities.
It's like a constant cycle of exploration, discovery, and improvement.
Exactly. Another key takeaway is that the success of neural networks is closely tied to the availability of data and computational power. As we've seen, the availability of larger data sets and more powerful computers has fueled the development of increasingly complex and capable models.
So the progress we've witnessed in neural networks is not only due to algorithmic advancements, but also to the exponential growth in data and computing power.
Precisely. And as data continues to proliferate and computing power continues to increase, we can expect even more remarkable advancements in the field of neural networks in the years to come.
Now that we've traced the historical evolution of neural networks, Let's shift our focus to understanding the fundamental building blocks of these powerful systems.
That's a great idea. To grasp how neural networks work, we need to delve into their inner workings and understand the basic components that make up these intricate systems. A good starting point is to think of a neural network like a team of specialists working together to solve a complex problem.
Okay, I like that analogy. So each specialist would represent a single neuron in the network.
Exactly. Each neuron, like a specialist, has a specific role to play in processing information and contributing to the overall solution.
And how do these specialists or neurons communicate with each other?
They communicate through connections. You can think of them as channels for exchanging information. Each connection has a weight associated with it, representing the strength or importance of that particular connection.
So the weights determine how much influence one neuron has on another.
Precisely. Just like, a senior specialist's opinion might carry more weight than that of a junior specialist, connections with higher weights have a greater impact on the flow of information.
That makes sense. Now, how are these neurons organized within the network?
They're organized into layers, much like the different departments or teams within an organization. The first layer is called the input layer.
So that's where the raw data enters the network, right?
Exactly. For example, if we're talking about image recognition, the input layer would receive the pixel values of the image. Each neuron in the input layer represents a single pixel.
And what happens to the information once it reaches the input layer?
It's then passed on to the next layer, which is called a hidden layer.
Why is it called a hidden layer?
Well, it's called hidden because it's not directly connected to the outside world, unlike the input and output layers. It's where the real magic happens, where the network learns to extract meaningful features and patterns from the data.
So the hidden layer is like the engine room of the network, where the heavy lifting takes place.
Exactly. There can be multiple hidden layers in a network, each progressively extracting more complex and abstract features from the data.
And what happens after the information has been processed by the hidden layers?
It's then passed on to the final layer, called the output layer.
So that's where the network delivers its answer or prediction.
Exactly. The form of the output layer depends on the specific task the network is trained for. For example, in a classification task, the output layer might consist of neurons representing different categories, and the neuron with the highest activation would indicate the predicted category.
This layered structure, with information flowing from the input layer through the hidden layers to the output layer, forms the basic architecture of a neural network.
It does, but the architecture itself is just the framework. What brings the network to life is the process of learning.
We've talked about learning in general terms, but how does it actually occur within the network?
Learning in a neural network involves adjusting the weights of the connections between neurons, to improve the accuracy of its predictions.
So it's like fine-tuning the communication channels between the specialists to ensure they're sharing information effectively.
Exactly. The network learns from its mistakes by comparing its output to the desired output, and then using this error signal to adjust the weights.
And this adjustment process is where backpropagation comes in.
Precisely. Backpropagation is the algorithm that calculates how much each weight should be adjusted based on the error signal. It propagates the error back through the layers, fine-tuning the weights to improve the network's performance.
So backpropagation is like a feedback mechanism, guiding the network towards making better predictions.
Exactly. It's an iterative process, with the network constantly adjusting its rates based on the feedback it receives, gradually improving its accuracy over time.
Now, you mentioned that each connection has a weight associated with it. What determines the initial values of these weights?
The initial weights are typically assigned randomly. This is because we don't know beforehand which connections will be most important for the task at hand.
So it's like starting with a random configuration of specialists and letting the network figure out the optimal communication structure through learning.
Exactly. The learning process essentially involves finding the optimal set of weights that allows the network to perform the desired task accurately.
This brings up another important concept: activation functions. You mentioned earlier that activation functions play a crucial role in introducing nonlinearity into the network. Can you elaborate on why nonlinearity is so important?
Sure, without nonlinearity, a neural network would essentially be a linear model, limiting its ability to represent complex relationships in the data.
Can you explain what you mean by linear and nonlinear relationships?
Well, a linear relationship is one where the output changes proportionally to the input. Think of a straight line on a graph. A nonlinear relationship, on the other hand, is one where the output doesn't change proportionally to the input. It might curve, bend, or have other complex shapes.
So most real-world phenomena involve nonlinear relationships.
Exactly. The world is full of complex interactions and dependencies that can't be captured by simple linear models. That's why nonlinearity is so important in neural networks. It allows them to model the intricacies of real-world data.
And activation functions are the key to introducing this nonlinearity.
Precisely. Activation functions are applied to the output of each neuron, introducing a nonlinear transformation that allows the network to learn complex patterns.
Could you give some examples of commonly used activation functions and how they introduce nonlinearity?
Of course. One popular function is the sigmoid function. It squashes the output of a neuron into a range between 0 and 1, introducing a smooth-shaped curve. This nonlinearity allows the network to model probabilities and make decisions based on thresholds.
So the sigmoid function is like a dimmer switch, controlling the intensity of the signal passing through a neuron.
That's a good analogy. Another commonly used function is the ReLU, or rectified linear unit. It's a simpler function that outputs the input directly if it's positive and 0 if it's negative.
So it acts like a gate, blocking negative signals and letting positive signals pass through.
Exactly. ReLU is known for its computational efficiency and its ability to address the vanishing gradient problem, which can hinder the training of deep networks.
We've encountered the vanishing gradient problem before. It can make it difficult for the network to learn effectively, right?
Exactly. ReLU helps to mitigate this problem by ensuring that gradients don't become too small during backpropagation.
There are also variations of ReLU, like leaky ReLU and ELU, which aim to address potential issues with ReLU while retaining its benefits.
Precisely. These variations introduce small, non-zero slopes for negative inputs, preventing neurons from becoming completely inactive during training.
So it's a family of activation functions, each with its own strengths and weaknesses.
Exactly. The choice of activation function depends on the specific task and the characteristics of the data. There's no one-size-fits-all solution.
Now let's talk about another fascinating aspect of neural networks: memory. We've mentioned before that certain types of networks, like recurrent neural networks or RNNs, possess a form of memory that allows them to process sequential data effectively.
Right. Memory is a crucial capability for tasks where the order of events matters, such as understanding a sentence, predicting stock prices, or generating music.
Can you remind us how RNNs differ from the feed-forward networks we discussed earlier?
Sure. In feed-forward networks, information flows in one direction, from the input layer through the hidden layers to the output layer. In RNNs, however, there are connections that loop back on themselves, allowing information from previous inputs to persist and influence the network's output.
So it's like having a feedback loop within the network, allowing past information to inform present processing.
Exactly. This feedback loop gives RNNs a form of memory. They can remember previous elements in a sequence, allowing them to understand context and make predictions based on past events.
Can you give us an example of how this memory capability is used in practice?
Certainly. Imagine we're trying to predict the next word in a sentence. An RNN would process the sentence word by word, remembering the previous words it has seen. This memory of the context allows it to make more accurate predictions about the next word.
So it's like the network is reading the sentence and keeping track of the story so far, allowing it to anticipate what's coming next.
Exactly. This ability to process sequential data makes RNNs particularly well suited for tasks involving natural language, time series, and other types of sequential information.
However, we've also discussed that early RNNs faced a challenge known as the vanishing gradient problem, which hindered their ability to remember information over long sequences.
That's right. The vanishing gradient problem occurs because gradients can become very small during backpropagation, making it difficult for the network to learn long-term dependencies.
So the memory of the network fades over time, like a leaky bucket.
That's a good analogy. To address this problem, researchers developed specialized units called gated units.
We've encountered two prominent examples: long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs.
Exactly. LSTMs and GRUs are designed to selectively control the flow of information through the network, allowing them to retain important information over extended periods.
So they act like gatekeepers, deciding what information to remember and what to forget.
Precisely. These gated units have revolutionized how we process sequential data, enabling significant advancements in natural language processing, speech recognition, and other tasks involving time series.
Now let's delve into a concept that has become synonymous with the remarkable progress in AI in recent years: Deep learning. We've mentioned deep learning before, but can you elaborate on what it is and why it's so important?
Deep learning, it simply refers to the use of neural networks with multiple hidden layers.
So it's about going deeper into the network's architecture.
Exactly. This depth allows the network to learn hierarchical representations of the data, enabling it to extract increasingly complex features.
Can you give us an example of how this hierarchical learning works in practice?
Imagine we're training a deep neural network to recognize faces. The first hidden layer might learn to detect simple edges and lines. The second hidden layer might combine these edges and lines to recognize shapes like noses and mouths. Subsequent layers might then combine these shapes to recognize entire faces.
So each layer builds upon the representations learned by the previous layer, progressively extracting more complex and abstract features.
Exactly. This hierarchical approach allows deep neural networks to achieve remarkable accuracy in tasks that were previously considered too challenging for traditional machine learning algorithms.
It's fascinating how this concept of depth has unlocked the potential of neural networks.
It has. The ability to learn hierarchical representations is one of the key reasons why deep learning has been so successful in various domains, from image recognition and natural language processing to speech synthesis and machine translation.
Now, let's shift our focus to a fundamental concept that underpins the power of neural networks, the universal approximation theorem.
Right. The universal approximation theorem is a mathematical theorem that states that a feed-forward neural network with a single hidden layer containing a sufficient number of neurons can approximate any continuous function.
That sounds like a very powerful statement.
It is. This theorem highlights the incredible flexibility and representational power of neural networks.
Can you break down what the theorem means in simpler terms?
Sure. Imagine you have a complex relationship between some inputs and some outputs. For example, you might want to predict the price of a house based on factors like its size, location, and age. The universal approximation theorem tells us that, in theory, you can build a neural network with a single hidden layer that can accurately represent this relationship, no matter how complex it is.
So it suggests that, given enough neurons, a neural network can learn any mapping between inputs and outputs.
Precisely. Of course, in practice, there are limitations due to factors like the amount of training data, the architecture of the network, and the optimization algorithms used. But the theorem provides a theoretical foundation for the remarkable capabilities of neural networks.
It gives us confidence that, with enough data and the right design choices, neural networks can learn to solve an incredibly wide range of problems.
Exactly. The universal approximation theorem is a testament to the power and potential of neural networks as universal function approximators.
Now, having explored the core concepts of neural networks, let's take a closer look at how these powerful technologies are being applied across various industries.
Neural networks have permeated virtually every sector, revolutionizing how we approach complex tasks and driving innovation across the board.
So neural networks are being used to improve healthcare outcomes and manage finances. But what about transportation?
Yeah, neural networks are playing a starring role in autonomous vehicles. They're the brains behind self-driving cars. They enable them to perceive their surroundings, make decisions, and navigate, safely and efficiently.
I can imagine how object detection would be a crucial capability for autonomous vehicles.
Absolutely. Convolutional neural networks, they're used to identify pedestrians, other vehicles, traffic signs, obstacles. They provide the car with a detailed understanding of its environment.
So they're constantly scanning the surroundings and identifying everything around the car.
Precisely. This information is then fed into decision-making algorithms, which also rely heavily on neural networks.
So neural networks are involved in both perception and decision-making.
Exactly. They work together to enable the car to make safe and efficient driving decisions.
It's remarkable to think that these networks can handle the complexities of driving, a task that requires split-second judgments.
It's a testament to the power of deep learning and the ability of neural networks to learn from vast amounts of driving data, including real-world experiences and simulations.
It sounds like self-driving cars are pushing the boundaries of what's possible with AI.
They are. And while there are still challenges to overcome, like handling unpredictable situations and ensuring safety in all conditions, the progress in autonomous driving is undeniable.
Now let's move on to another field that's being revolutionized by neural networks: Natural language processing, or NLP.
Yeah, NLP focuses on enabling computers to understand, interpret, and generate human language. And neural networks have become, indispensable tools in this field.
We've seen incredible progress in NLP in recent years, with applications like machine translation, chatbots, and voice assistants becoming increasingly sophisticated.
Absolutely. One key area where neural networks have made a significant impact is machine translation.
I've noticed that translation services have become incredibly accurate in recent years. What's driving this improvement?
Well, the advent of transformer models, which we discussed earlier, has been a game changer for machine translation.
Can you remind us how transformers differ from previous architectures?
Sure, transformers, they employ self-attention mechanisms, which allow them to process entire sentences simultaneously, capturing long-range dependencies and understanding the context of words more effectively.
So they're able to see the bigger picture, rather than processing words in isolation.
Exactly. This has led to significant improvements in translation quality, making it easier for people to communicate across language barriers.
What other applications are there in NLP?
Neural networks are also being used to develop chatbots and virtual assistants that can understand our queries and provide helpful responses.
It's amazing how these virtual assistants can understand our spoken commands and even carry on conversations.
It is. The progress in speech recognition and natural language understanding, powered by neural networks, has made these interactions more natural and seamless.
What other exciting applications are there in NLP?
Well, neural networks are being used for text summarization, sentiment analysis, question answering, and even creative writing, demonstrating their versatility in handling various aspects of human language.
It seems like neural networks are pushing the boundaries of what's possible in NLP, enabling computers to interact with language in ways that were previously unimaginable.
They are, and as these technologies continue to evolve, we can expect even more sophisticated applications to emerge, blurring the lines between human and machine communication.
Finally, let's wrap up our discussion of applications with a look at deep reinforcement learning, which combines deep neural networks with reinforcement learning principles.
Deep reinforcement learning has emerged as a powerful approach for training agents to learn complex tasks through trial and error, achieving remarkable results in various domains.
We discussed AlphaGo earlier, which was a groundbreaking example of deep reinforcement learning.
Exactly. AlphaGo demonstrated the potential of this approach by mastering the game of Go, a game of immense complexity that had long been considered a challenge for AI.
How does deep reinforcement learning work in practice?
It involves an agent interacting with an environment and receiving rewards or penalties based on its actions. The agent uses a deep neural network to learn a policy, which maps states to actions, aiming to maximize its cumulative reward over time.
So it's like learning by doing, with the agent refining its strategy based on the feedback it receives from the environment.
Precisely. This approach has been successful in training agents to play games, control robots, optimize traffic flow, and even design experiments, demonstrating its versatility and potential impact.
It seems like deep reinforcement learning is pushing the boundaries of what's possible with AI, enabling agents to learn complex tasks in a way that resembles human learning.
It is. And as research in this field progresses, we can expect even more impressive demonstrations of AI capabilities blurring the lines between human and machine intelligence.
Now, having explored the fascinating world of neural networks, from their historical evolution to their diverse applications, let's take a moment to acknowledge the challenges and ethical considerations associated with this powerful technology.
That's an important point. While neural networks offer immense potential to solve complex problems and improve our lives, they also present certain challenges and raise ethical concerns that we must address responsibly.
Let's start by discussing the technical challenges. What are some of the hurdles that researchers are working to overcome?
Well, one challenge is the vanishing and exploding gradient problem, which we've touched upon earlier.
Can you remind us what this problem entails?
In deep neural networks, the gradients used to update the weights during backpropagation can become extremely small or large as they propagate through the layers.
So the error signals either fade away or amplify too much, making it difficult for the network to learn effectively.
Precisely. This can hinder the training of very deep networks, limiting their ability to learn complex representations.
Are there any solutions to this problem?
Researchers have developed techniques like normalization, residual connections, and gated units to mitigate the vanishing and exploding gradient problem.
Can you briefly explain how these techniques work?
Normalization, it helps to stabilize the gradients during training, preventing them from becoming too extreme. Residual connections allow gradients to bypass certain layers, facilitating their propagation through deep networks. And gated units, like those found in LSTMs and GRUs, selectively control the flow of information, helping to preserve gradients over long sequences.
It sounds like these techniques are crucial for enabling the training of deep and complex networks.
Absolutely. They have played a vital role in the advancements we've seen in deep learning.
What other technical challenges are researchers grappling with?
Another challenge is the computational resource demands of training large neural networks.
I can imagine that training these massive models would require significant computing power and energy.
It does. Training large models can be very expensive and time-consuming, especially for complex tasks like natural language processing and image generation.
Are there any efforts to address this challenge?
Yes. Researchers are constantly working to develop more efficient algorithms and specialized hardware that can accelerate training and reduce energy consumption.
So there's a push to make deep learning more accessible and sustainable.
Absolutely. Another technical challenge is the explainability of neural network decisions.
What does explainability mean in this context?
Neural networks are often seen as black boxes, meaning it can be difficult to understand why they make certain decisions.
So we might know that a network is accurate, but we don't fully understand its reasoning process.
Exactly. This lack of transparency can be a concern, especially in sensitive applications like healthcare and finance, where understanding the basis for decisions is crucial.
Are there any efforts to make neural networks more transparent?
Yes, the field of explainable AI, or XAI, is gaining traction. Researchers are developing techniques to interpret model decisions, providing insights into the features and patterns that influence the network's output.
So XAI aims to shed light on the black box and make neural networks more understandable.
Precisely.
Now let's move on to the future. What are some of the research trends shaping the evolution of neural networks?
The field of neural networks is constantly evolving, with researchers exploring new frontiers that promise to push the boundaries of AI even further.
What are some of the most exciting research directions?
One promising trend is self-supervised learning, which allows models to learn from unlabeled data, reducing the need for expensive and time-consuming manual annotation.
So these networks can learn from raw data without explicit instructions.
Exactly. This opens up vast new possibilities for training models on massive data sets that were previously inaccessible due to the lack of labeled data.
What other trends are worth mentioning?
Federated learning is another exciting area of research. It allows models to be trained across decentralized devices, such as smartphones and edge devices, without sharing the raw data.
So we can leverage the collective data power of millions of devices while preserving user privacy.
Precisely. Federated learning has the potential to revolutionize personalized AI, enabling models to be tailored to individual users without compromising their data.
What other trends are shaping the future of neural networks?
Well, neuromorphic computing is an emerging field that aims to develop hardware that mimics the brain's neural architecture, potentially enabling more efficient and powerful AI systems.
So instead of running neural networks on traditional computers, we'd have specialized hardware designed specifically for these tasks.
Exactly. Neuromorphic computing holds the promise of achieving human-level intelligence in a more energy-efficient and scalable manner.
That sounds incredibly futuristic. What other research avenues are being explored?
Quantum machine learning is an intriguing field that explores how quantum computing can be used to accelerate neural network training and inference.
So by harnessing the principles of quantum mechanics, we could potentially train and run neural networks at speeds that are currently unimaginable.
Exactly. Quantum machine learning is still in its early stages, but it holds tremendous potential for revolutionizing the field of AI.
It's fascinating to see how these research trends are pushing the boundaries of what's possible with neural networks.
These advancements are not only expanding the capabilities of AI, but also raising profound questions about the nature of intelligence and the future of our relationship with technology.
It seems like we're on the cusp of a new era of AI, driven by the incredible power of neural networks.
We've only just begun to explore the vast potential of these technologies. As they continue to evolve, they will undoubtedly shape our world in profound and unpredictable ways.
As we conclude our deep dive into neural networks, it's clear that we've only scratched the surface of this complex and rapidly evolving field.
It's true. From their humble beginnings as simple mathematical models to their current status as powerful engines driving innovation across industries, neural networks have come a long way.
And the journey is far from over. With ongoing research pushing the boundaries of what's possible, the future of neural networks promises to be even more transformative and awe-inspiring.
As these technologies continue to evolve, it's crucial that we engage in thoughtful discussions about their ethical implications, ensuring that they're used responsibly to benefit humanity.
We've covered a lot of ground today, from the history and inner workings of neural networks to their diverse applications and the challenges and opportunities that lie ahead.
I hope this deep dive has provided you with a deeper understanding of this fascinating field and sparked your curiosity to explore further.
The world of neural networks is full of possibilities. As we move forward, it's up to us to shape the future of AI in a way that benefits all of humanity.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.